Hey, we've still got a few people rolling in, but maybe we'll kick things off. Hey, thanks everyone for tuning in. It's a real pleasure today to have Jeff Burghardt and Tim Johnson speak to us. And Jeff he's an earth scientist at Pacific Northwest National Laboratory. And with that, he has 12 years of experience in hydraulic fracturing research and over 15 years in experimental and computational geomechanics. His PhD was from the University of Utah, and his dissertation work focused on modeling large deformation and high-rate constitutive behavior of rocks and soil. After his degree, he spent 5 years working in R&D and operations for Schlumberger, and he was the technical lead of several large interdisciplinary research projects, and those focused on hydraulic fracturing and joining. In 2016, he joined PNNL, and he has continued to work on experimental and computational geomechanical research. Sharing the stage with Jeff today is Tim Johnson. And Dr. Johnson is a computational geophysicist at the Pacific Northwest National Laboratory, and he is internationally recognized for his contributions towards characterizing and monitoring subsurface properties and processes using autonomous geophysical measurements with an emphasis on electrical measurements. So I'm going to turn it over to Tim and to Jeff, and please go ahead.
You're going to start us off, Jeff?
We lose Jeff?
Yeah, I'm back. Okay, so
okay.
crashed for some reason. Sorry. Great timing.
Yeah.
All right, we're up.
Yes, you are indeed, Jeff. I gave a long
Okay, I turn off my video because sound is a little garbled. Can you hear me okay?
Yes.
Okay, great. I didn't hear what you said, but I'll go ahead and start. Yeah, thanks everyone for joining. It's nice to see a lot of familiar names. I have not talked to you in quite a while on the call. So we'll be presenting some work Tim Johnson and myself have been developing. Say Tim has done most of the heavy lifting here. But I think we've made some major breakthroughs in the last couple of years on imaging hydraulic fractures, and particularly the stress field around hydraulic fractures with electroresistivity tomography. So I'll present a little bit of the background here and introduce some of the concepts of ERT, because I think many in this community may not be familiar with it. I wasn't until I started working with Tim. And then we'll show several field tests that we've done to demonstrate this. Tim, go ahead and advance slides. Okay, so as I mentioned, we'll start with just some of the basics of time-lapse electroresistivity tomography, sometimes called 4D electroresistivity tomography because it's time and space. Talk briefly about the relationship between stress and electroresistivity. We're focusing here on crystalline rocks, where most of the porosity is in fractures of various scales, which is where this relationship between stress and resistivity is quite strong in some circumstances. And then Tim will present several field tests that we did as part of the EGS Collab project at 2 different test beds there, and some very recent results we did that we just published very recently. Yeah, we'll talk about conclusions and caveats. So first, basics of electroresistivity tomography. So I've diagrammed here our continuum blob. So the colors here would represent a field of resistivity. So the stars would be where we're injecting current. So from into the black star, out of the red star in this case. And just for conceptual illustration, I've shown these streamlines would be like the current lines. And of course, the shape of those current lines would be dependent on the shape of the underlying resistivity field. But and there's several different types of measurements that can be made, but this is kind of the simplest to explain. So inject current on 2 electrodes, then measure the voltage or the potential on 2 other electrodes that can be spaced kind of anywhere. And Tim will show some great examples of pairs that were more informative and less informative in our surveys. But by injecting current at different locations and measuring the potential at different locations, you can characterize different portions of the resistivity field and also how the current flows. And as with other tomography techniques, so you characterize many different paths here, and then you can use inverse methods to invert for the underlying field if you have enough measurements. And so what I'm showing here is a static baseline field. So this is not time-lapse resistivity. This would be how you characterize a static existing resistivity field. Let's go to the next slide. So for time-lapse, and tying specifically here to a hydraulic fracture, we would start with this base resistivity field to do a baseline survey and invert for the baseline field. And actually you don't even need to necessarily invert for the base field. It's the baseline measurements. So what are the potentials for the given current injection locations? And then something changes. So this can be injection of fluids, which is what this technique's often been done for. But if we have a hydraulic fracture open up, there are 2 things here that I'll illustrate. So if we ignore stress for a minute, in the center image, and we just have a fracture open and it's filled with a fluid. Often the fluids injected would be have a higher conductivity, electrical conductivity than the surrounding material. So this would alter the resistivity field, alter how the potential and the current flows. So I've kind of shown the altered streamlines here, or current lines. And so just due to the conductivity of the fluid in the fracture, that would be altered, and we would see some difference. So we would inject the current, measure the potential, and at a later time after something has changed, we would make the same measurement, and there would be a difference, right? And then on the figure on the right, it's just another example of, so this is a combination of the fluid filling the fracture, which itself would alter the resistivity field. But then also, as we know, there's a shadow zone, or a zone of increased compression around the fracture since it's opened. And as we'll show on a future slide, in specifically crystalline rocks, increased compression leads to decrease in resistivity. So we would expect some region around the fracture where the resistivity goes down compared to the baseline field. And so that would also, of course, alter the current lines and the potential. And that measurement that we're looking and repeating will change. Okay, next slide, Tim. Okay, so with time-lapse ERT, what we invert for the measurement that we invert is the difference between, say, the voltage measurement, current measurement pairs between one time and the next. And that allows us to essentially subtract out that baseline field. And what we invert for is just the anomaly that occurs from time 1 to time 2. So in this case, we would invert for, this change, the things that change the resistivity with time, which the 2 mechanisms I talked about are the increased conductivity due to the fracture itself and the decreased conductivity due to this stress shadow around the fracture. And when we first started this, we were mostly thinking of the fracture itself and the change in fluids in the fracture as being what we were expecting to see. But as we'll see in the field test, we'll show what we end up seeing much more is the stress shadow around the fracture. So we image the fractures primarily as a result of by seeing the stress shadow around the fractures. All right, next slide. Okay, and so I'll just talk about this, and I think I'll transition it over to Tim after this. So these are just some examples from the literature of different rocks. Again, also crystalline rocks, relatively low porosity, and just fractures of everything from grain boundary scale fractures to larger fractures. But I think most of these rocks are westerly granite and such are familiar to this community. They're relatively homogeneous, so we're not talking for the most part about really large scale natural fractures, although we think some of those are present in our field tests, as we'll talk about. But this shows just simply the resistivity of the sample versus confining pressure. Now, these are all under hydrostatic confinement, but you can see there's a clear dependency, and it's more pronounced at lower confining pressures. And generally, the sensitivity of stress and resistivity goes down with higher confining pressures, but it's still there. And also worth noting, these are all saturated rocks, so the saturation, even in these really low porosity rocks, has a strong impact on the resistivity, because for the most part, the electrical conductivity is mostly takes place through the fluids. All right, Tim.
Okay, am I taking over from here, Jeff?
Yep.
Okay, I'm at the lab, so I'm gonna go ahead and turn my video on. If there are issues, somebody speak up and I'll turn it off again. So I just wanted to add to Jeff's discussion on this. One easy way to think about this relationship between confining pressure and resistivity is shown here is what the electrical resistivity that we're measuring is really sensitive to is the porosity of the rock. So when you put it under confining pressure, the microfractures compress and you lose some porosity, and the current is flowing through the pore spaces primarily. And so when you lose porosity, the resistivity goes up or the conductivity goes down, which is actually what we're measuring. When a fracture opens, you get a flow path for current, and so the conductivity goes up or resistivity goes down. So Jeff presented everything here in resistivity. What we're actually going to show the inversions in is conductivity, which is just the inverse or the reciprocal of resistivity. So which slides here if we can. So the experiments that were conducted were part of the EGS collab project that was funded by GTO. Tim Nisi was the PI. And this is at the Sanford Underground Research Facility, which was formerly the Homestake mine. So we had two test beds here. One was on the 4850 level, and one was on the 4100 level. And we're going to start with an experiment we did on the 4100 level to kick things off. So this is was our first experimental test bed. We have the mine drift here. And then we had several subhorizontal wells drilled off of the mine drift, and the direction of those wells was because we were going to hydrofracture. We were anticipating the hydrofractures to have an orientation as shown here in the shaded areas. So all of the yellow wells here are monitoring wells. They were grouted in place. They had thermistors and fiber and geophysical instrumentation. And then we had the injection well, this is the green well here, or the well that we the hydrofractured, and then our production well here. And our objective was to establish flow pathways between the injection to the production well, and then have this highly monitored network to better understand how the hydrofracturing worked and how the flow system worked. So in the grouting boreholes, we had active seismics. This was LBNL's chasm system. We had passive seismic ERT electrodes that I'll show you, distributed temperature, and then we also had some discrete thermistors. So we're going to focus on the stimulation that we did in this notch, which was very, very close to these two monitoring wells. And yeah, so let me go to the next slide here. So this is just some quick images of what our instrumentation strings in the grouted or the monitoring wells look like. So here's some pictures of us installing them. We had hydrophones, everything was in, and ERT electrodes is shown here. The electrodes were just a stainless steel mesh that were strapped to a PVC spine. And then we inserted everything into the borehole and grouted it in place. Hoping that the grout seal would protect all of the equipment from the high pressures and that it wouldn't leak, and that didn't turn out to be the case at all. That was a lesson learned. But there were some consequences of that in terms of the ERT images that I'll show you shortly. So this is focusing on the ERT array. The electrodes in each of the monitoring wells are shown here in red dots. They were at 3 meter spacing in all of the wells. And they were kind of designed to image this area in here. You know, you can read some of the specs here. When we would run these system ERT systems, they run when you're in monitoring mode, they just run continuously. They'll collect a survey, which is a set of measurements, 1498 in this case. And that takes about 34 minutes. So your time resolution between images here as the process is going on is about 34 minutes in this case. And these would run continuously as we were doing these fracture and flow experiments. So Jeff mentioned baseline images. These are the baseline images on the 4850 that we collected before we did any fracturing or experiments. You're looking at these from different directions. So here it's as though you're standing in the drift looking toward our test bed imaging site. And I've superimposed some red blue lines here just to kind of show the folded structure here that we kind of expect in this metamorphic rock. And here shows some superimposed with some of our logging data. In resistivity, things match very well. And then very importantly, I've superimposed here where the natural fracture zones are. These were identified through oriented cores that we took from each of these wells. And there were 2 very prominent and well-developed fracture zones. And this one in particular on the right is very important, as you'll see for the experiments that we conducted. And that's shown here. So here's the 164-foot notch where we hydrofractured, and we expected, based on the stress measurements, for the fracture to be oriented thus to intersect these wells. And then shown here in blue are those natural fractures that I just mentioned. So when we did this experiment and injected flow into the fracture, we actually ran a camera down this production well, and you could see where the fracture had degenerated and jets flowing in to this well over, I think it was about a 2 meter interval. There were several different water jets intersecting this well, which was neat to see. And then when we did flow tests and we injected on this fracture after some time, we started getting, we got DTS signals in these wells. And I'll show you the ERT signals were also strong. And we also started to get water coming into the drift along this profile, along the same natural fracture path. So we had a lot of different data saying that we were getting flow into this natural fracture zone that had been intersected by our hydrofracture here. So this is a really busy slide. I'll walk you through it, but the intent here is to show the sensitivity of the ERT data to the injection interval pressure and the flow rate. So again, let me just go back. We had packed off this interval, and we're pressurizing this hydrofracture here. So the pressurized interval is right here where this pink dot is on these slides. So what I'm showing here are different measurements, ERT measurements down. You start down here at the bottom. Here's the time series of the interval pressure and the interval flow rate as we were conducting some tests. And the reason these vary like they do is because we were looking at different, basically exploring different regimes and making changes based on what we saw. So what I'm showing here are these are the raw ERT data that we're measuring as the pressure and flow change in the interval. The first one here. So the hydrofracture is just on the other side of these two monitoring wells in this case. And I'm just showing here, we're injecting on these two electrodes and measuring potential across these two electrodes in this case. And then in this case, they're just shifted deeper in the boreholes. And I won't get in too much into the sensitivity distributions here, but if you look at these profiles, they're basically mirror images of each other. And that's just because of the sensitivity distribution changes when you shift that measurement down deeper into the borehole. But the bigger point, and the inversion takes all of that into account and takes care of that when it makes the images. But what we see here is when we start injecting, we immediately get a really strong response. And then as pressure and flow rate change, just along these lines, we get these really, these measurements are very sensitive to what the pressure and flow are doing in the injection interval. If we move to electrodes on the other side of the monitoring system that are farther away from the hydrofracture, the systems are more muted. They're less sensitive to what's going on. So the main point that these graphs are trying to make is that close to the hydrofracture, we're seeing a lot of activity in the ERT responses, and farther away the responses take, they're more muted and they take longer to respond when we start running these tests. And these are just 4 measurements out of the approximately 5,000 that we take over the course of 36 minutes, whatever it is. So we invert the data at each one of these times, and that's what I'm going to show here. So here's the same pressure and flow rate sequence. Our hydrofracture is here. Our natural fracture system is here. And it's also over here. So what this grayed out area are actually elements in the inversion in the modeling mesh that they're grayed out because they're insensitive. And the reason they're insensitive is because the monitoring borehole back here, we lost. All the electrodes basically, it was intersected by high pressures, and we lost all the electrodes, and that removed the sensitivity to this lower part. So all of the insensitive cells are grayed out. So I'm going to run this animation that shows the time-lapse images, and then on the next slide, I'll spend more time describing what we're actually seeing. But what you're going to see is you're going to see a big increase in conductivity in the natural fracture zone. That's happening because the fractures are being pressured up and opening, and that causes a big flow paths for current and an increase in conductivity. And you'll also see some shadow stresses develop in between these zones that pressure up when we start injecting. So here we're starting to inject. You see the natural fracture zone increase in conductivity as it pressures up. And then you see this decrease in conductivity here. And if I could stop it there, these are the shadow stresses that Jeff was mentioning. So as these fractures pressure up, they're putting compressive stresses adjacent to the fractures. And you get this decrease in conductivity because the porosity is decreasing slightly. And then you presumably we're getting water pushing up into here and some fractures. So there are a lot of details here. We did some shut-in tests and then started things up again. But I'll just run this to the end, and then we'll talk about it more on the next slide. Okay, so we ran this for about a week after we stopped the testing. You can see that it was from October 25th to November 7th or so when this test ran. An interesting thing that I don't think I show on the next slide, that is even after 7 days, this is when the pressure was taken off the hydrofracture. these fractures are still open. There's still a lot of increase in conductivity. So presumably the hydrofracture shut and it kind of locked everything in. And it took a long time for all this water to drain from the system and for the fractures to return to their pre-test state in terms of the aperture. They were hydropropped for a while. Okay, go to the next slide. Okay, so just quickly what we're seeing. So each one of these 6 images here, the time for each one of those is shown down here on the bottom. So in A is right after we started injecting, you almost immediately see a response in the natural fracture system. And we don't think this is actually flow because we weren't injecting that much, filling these fractures. It's more likely these fractures are just being pressured up and opening. And that increase in porosity is causing this increase in conductivity. And you're starting to see some shadow stresses next to this opening. You also see some opening of the natural fracture system down here, which suggests that this fracture ran over this far and was, pressurizing those fractures. That continues over time here in B. Conductivity increases, presumably fractures are opening, and the shadow stress zone in between these 2 regions grows, and that continues on to C. At D, these compressed zones, the shadow stress zones seem to start to bifurcate, and that, if you watch the sequence, it seems to be that water is moving, or pressurized water is moving up into these fractures and possibly opening fractures here. And that continues to E. Actually, when we did the shut-in test, it looks like pressurized, water from here moved up into these fractures more, and you get this bigger bifurcation of that shadow stress zone. And then when we start things up in F again, you see these fractures opening again a little bit. So I'm not going to, just for time's sake, walk through the whole sequence that all the way through here, but it gives you an idea of what we're seeing with the ERT imaging and how it's describing what's happening with these fractures and also the stress in our test bed as we were conducting this particular test. So I'm going to move now to the 4100 level and just describe what the first testing that we did in the 4100 level. That test, the first test we did was aimed at seeing if we could shear stimulate the test bed on the 4100 level. So this is what the drift looks like. Again, the boreholes, the yellow boreholes were grouted in place, just like last time, the same type of instrumentation. And all of these other boreholes were left open in this case. And so what we did was we went to the central borehole and we packed it off and then pressurized the interval to just below the minimum principal stress in an attempt to get fractures, natural fractures. These were all closed in, but you could see them on the logs, basically trying to get them to open to see if we could shear slip these fractures. That didn't work, as we'll show, and Jeff can talk more about. But anyway, we did these shear tests in each one of these intervals in this borehole. And while we were doing the shear tests, we were monitoring what we saw with the ERT and with the other sensing modes also. So down here is a picture. If you're standing in the drift down here and looking northward up the drift, this is what it looked like before we had all of the instrumentation, the flow, instrumentation and monitoring in this part as we were building up the system here. It gives you an idea what that test bed looks like though. So here's a typical example of a shear stimulation test. The black is the interval flow rate and the red is the interval pressure. So this first period of what you're basically seeing here is the interval being pressured up, and then Jeff would hold it there for 30 minutes to an hour to see if there was any change in interval pressure or increase in flow rate that would indicate that we might have had a shear slip. And That never happened. As you can see, there's no real change here. And the flow rate into the zone was very, very, very small. But what we did do is exert pressure on the borehole walls and exert compressive stress on the rock around the boreholes, and that was all monitored with the ERT system. And that is what we're seeing here. So these are inversions. So basically during these tests, we collected data, and these are the inversion results for each one of the intervals. And so what you see are these decreases in conductivity around the pressurized interval, and they track where as we're moving up this borehole, they track very well. They're all centered on the pressurized interval. And so what we're seeing here is the decrease in conductivity caused by the stress bulb that's around this pressurized interval. And these tests are a really nice validation of what we are really seeing changes in, changes in stress, but it's really the change in porosity within that rock caused by the stress exerted by the packers and the pressurized borehole. And we hydrofractured this later, and I'm pointing out this feature right here, and these ones in this deeper in this well, because when we hydrofractured in this zone, the hydrofracture ran right through here. And so there was this more compliant zone suggested here that actually fractured later when we went ahead and pressurized that interval and made the hydrofracture. So that's shown here. These are just more of the hydrofracture or the shear stimulation test where this lobe develops. And then here is where we actually hydrofractured it. So these increases in conductivity that you're seeing here are being caused by fluid moving into the monitoring wells in each one of these cases. Well, monitoring well in this case, this borehole was open, TN. So we're injecting in this interval, and we verified from the fiber that the intersection of this fracture was right here. Can you see my mouse moving, my arrow? Jeff or John?
Yes.
Okay, good. So the fracture propagated from this isolated interval through here, and we don't actually see the fracture, the hydrofracture, in terms of the increase in conductivity is probably very small hairline fracture. And as Jeff mentioned, what we actually see is the stress that fracture causes, and that's this decrease in bolt conductivity here, and also along this borehole. And here's just an oblique view of that, where we're injecting here, the fracture runs through this region, and we're seeing a decrease we're seeing the shadow stress caused by the fracture rather than the fracture itself in that case. So that was it. Both of these papers, if you're interested in looking at them, the first 4850 has been published here, and this one is about to be published. It's in production right now. So just some take-home comments. We can monitor in crystalline rocks this imaging stress with ERT works very well because the fractures are compliant. Even the microfractures are they have large aspect ratios, so when we put stress on them, they tend to compress. It doesn't work as well in, say, sedimentary rocks where the pore spaces are more round because they don't compress as easy. I will say this method is scalable, so ERT works from very small scales to very large scales. Of course, resolution decreases as you get farther from electrodes, so that always has to be taken into account. For geothermal or deep applications, the downhole components are really robust. If you were to put these in the annulus, there are no moving parts. There are just wires, wires and electrodes, which can be made to handle high pressures and temperatures very well, if correctly designed. And we learned that lesson on the 4850. We typically use ERT to image fluid migration, and that's what the kind of the plan was when we first started in EGS collab, we thought we would be seeing the fluid migrating through the fractures. And we did do saline tracer tests where you can see, so you establish a flow field and then inject a saline tracer, and you can see that moving through the system also. And this is typically what we've used time-lapse ERT for in the shallow subsurface, is monitoring fluid flow. The biggest challenge to deep applications is that ERT doesn't work with metallic borehole casing. And of course, metallic borehole casing is everywhere in the deep subsurface, so it really limits what you can do with ERT there, but which is perhaps why we haven't seen more of it in the deep subsurface. But that's the primary difficulty with using ERT in geothermal applications, for example. So with that, that was our last slide. We're happy to take, Jeff and I, any questions you might have.
Thanks, Tim. I've been answering a few in the chat, but
Yep.
Okay.
Yeah, well, and maybe we can verbalize some of those. Yeah, Jeff's pretty fast answering the chat. So Jeff, why don't you just walk through the questions that have been posed and your answers to them?
Sure, we can do that. Yeah, so Ed Sieberts, hi Ed, nice to hear from you again. Asks if the physics dictate like how the imaging capability of the resistive ERT decays with distance. Is it something like 1/r? And he asks if we've looked at numerical models of the resistivity field process. And so the answer I gave is that yes, in general, the resistivity imaging kind of falls off at like 1/r. And Tim can add some nuance here. It depends on the spacing between the electrodes to a large degree. And I also mentioned that yes, that as part of the inversion process, Tim builds a numerical to find an element model to do the adjoint inversion. And we've been developing, but not yet published, a direct coupling with the fluid flow model to the ERT. So that was Ed's question. And Tim, if you have anything to add, feel free to jump in. And Zongyu Zai, hopefully I said that right, asks if the ERT technology has been experimented with or implemented in soft formations or unconsolidated sand, either in the laboratory or field, and how effective is it in these conditions compared to the performance in hard rock? And so my response was that ERT has been widely used, and I'd say mostly used in the shallow subsurface, and everything from unconsolidated soils to crystalline rock, as we're showing here. And so it works very well, although in the higher porosity, softer formations, the sensitivity to stress is just not the same as it is in the crystalline rocks that we've been showing here. Instead, the resistivity is much more sensitive to changes in the fluid saturation and the conductivity of the fluids. So it's effective, just it sees different things.
Yeah, I will say, I will add to that. So that's absolutely true. I mean, ERT was developed and really matured in the shallow subsurface in sedimentary systems for environmental applications mostly. There have been some papers as of late using ERT to monitor basically like compression of soils, in engineering applications and geotechnical applications, because as soils compress, of course, you get a decrease in porosity. So there are publications like that out there, especially as of late, but ERT's mostly been used, time-lapse ERT, to monitor, as Jeff said, changes in saturation or changes in fluid conductivity as say a contaminant plume moves through the subsurface or something like that. Or a tracer, injected tracer.
Yeah. So a few other questions I've not gotten to yet. So Gang asks how fast these stressed zones adjacent to the fractures decay and change after stopping pumping or at all. And I think you can see in some of these images they do decay with time, and and as Tim showed, and you know, in these rocks where outside of the fracture zones, the permeability is very low. It took quite some time, weeks in some cases, for these anomalies in the resistivity field to decay, but they did decay back roughly to something close to baseline. And then Tim, I'll pitch this question to you. So Olav Gustafsson asks, over what spatial scale could this method be applied?
Yeah, a common question. So we, you can, to answer this, I usually say if you were just to take one of those images that I showed and take a 0 off of the scale or add a 0 to the scale, you would get the same thing. So you can scale things up, but the anomalies that you see have to be bigger before you see them, because the anomalies would have to scale up also. You can also scale them down, and then the anomalies that you can see get smaller, so the resolution increases. So we've conducted surveys that are miles long, and seeing several hundred meters down into the subsurface from the surface. But of course, the resolution as you go deeper goes away, so the anomaly has to get bigger. So the way we approach this question usually is we try to model the process with either a flow and transport geomechanical model coupled to the ERT, and then basically you have the truth, and then you'd have an ERT image, a simulated ERT image, just to kind of investigate what you can see. And we always try to do that before we deploy anything in the field, so that everyone is on the same page in terms of what we're likely to see, what we can, and what we're likely not to see in terms of what we can resolve. So that's kind of a qualitative answer, but I hope it's good enough.
Well, I'm sure it is. So I'll ask a quantitative question then. I'm very intrigued at the change in resistivity with stress. Have there been experiments done to sort of quantify that or demonstrate that? And if so, are there possibilities to apply this to inferring in situ stress changes or modulus?
Yeah, so Jeff mentioned that we are in the process of developing a model that we've actually exercised a little bit that will it's basically a flow and transport and geomechanical model that also simulates the ERT response from that process, with the idea being that if we have a forward model like that, we can invert for rather than the change in electrical conductivity, the true change in stress directly from the ERT data. And so that's something that's just kicked off this year and that we're working on. But we're hoping will pan out, because the resistivity is very sensitive to stress. So I don't know,
Tim, if you want to flip
Yeah.
back to I think it was slide 3 or 4 that has those curves. Yeah, so because the power here is really in the time change, it's the time lapse.
Mm-hmm.
So I don't think we'll be able to determine the base stress field with this, because while there's probably some effect there, it's difficult to disentangle sort of the existing heterogeneity in the resistivity field from the stress field. So I think this is really powerful at seeing changes in stress. And to speak to the laboratory testing, we ourselves have not done any yet, although they're planned. We're working on it. So we're really kind of drawing from the literature to get the motivation of what, and to be clear, like, we're not using these curves, just we directly invert the data to find the changes in resistivity. But to infer quantitatively what the stress would be, we would need to make measurements like this on, say, core samples from the field that we're working in. And then, of course, there's questions of scaling. But Yeah, so this is, we're working on it, but we can't yet quantify the change in stress. I'd say the stress field changes are qualitative at this point, but we're working towards that.
That's awesome. Do we have any other questions? If so, just speak up.
So I see Ed Siebert's asks what the time resolution. So it's really limited by how. So there's this trade-off there that the more resistivity measurements we make as part of the tomography, in principle, the better the inversion, the better the resolution, but the longer it takes. So then we kind of lose some time resolution. So, and I think Tim mentioned the numbers here. It was 30 some minutes per survey for these examples. So it's kind of at that time resolution that we see things.
So yeah, that's true. I will add that a lot of the time resolution limitations are based on what your equipment can do. So in this case, we used an 8-channel system, which per current injection, you can measure 8 different potential electrode pairs. We are working on building a new system that's a 64-channel system, which would, you know, decrease the time by a factor of 8. So you'd get down to something like, you know, six minutes or so in this case between images.
That's fabulous. I don't see any other questions. So I really want to thank you both, Tim and Jeff. I mean, this was a really intriguing presentation, and I think you've made some great steps forward in the last little while. Fantastic. Thank you.
Yeah, happy to do it.
Thanks for having us.
Thanks for all the great questions.
Yeah. Thanks, everyone.
Thank you. Bye.
Bye.
Hey, Jeff, and I don't know, maybe Tim's gone, but man, that was really cool.
Thanks, John.
You know, I kept on thinking as I went through of something like a modified FMI tool where you could pressurize the wellbore and come up with properties just based on the change in resistivity. That is really, I mean, yeah, you guys have come a long way.
Yeah. You may recall, we're not recording, right? You may recall.
Oh, we are, but
okay.
no, hang on. Let me turn off the record.